Ancient space signal shocks scientists. Humanity detects a 10-second signal from the dawn of universe, the oldest supernova ever observed. Humanity has detected a mysterious 10-second signal from one of the most distant regions of the known universe, offering an unprecedented glimpse into the cosmos as it existed more than 13 billion years ago. Scientists believe the signal originated when the universe was just 730 million years old, making it one of the earliest stellar explosions ever recorded. Now it's time to go in detail and uncover the full story in today's AI podcast.
Okay, let's just jump right in. We are starting today's deep dive with something just incredibly specific, a single piece of cosmic data.
And when you say specific, you really mean it.
I do. We're talking about a 10-second signal. That is it. 10 seconds of ridiculously high energy light from a place that, honestly, it just stretches the limits of what we can even comprehend.
Right.
And this isn't some, minor astronomical footnote. This is a full-blown cosmic detective story. It's all centered on an event that astronomers are calling GRB 250314A.
And it's giving us this direct, truly unprecedented look back into the universe's infancy.
We really need to set the stage for you here to understand the scale we're dealing with.
The scale is almost everything. Our mission here is to unpack what this means, because this signal, it originated more than 13 billion light years away.
13 billion.
Which means the explosion itself happened when the universe was only about 730 million years old. So, when we say we're looking back in time, we mean it literally. We are peering into the cosmic dawn.
That's a universe that's what, maybe 5% of its current age?
Barely. That fraction is what's so stunning about this.
It's hard to even picture a universe that young. But, well, the data is the data. So for you, listening in, we're going to trace the path of this 10-second flash. We'll explain the science that caught it. And this is the really critical part. We'll get into the surprisingly modern things they found.
Right. And those findings are fundamentally challenging some of our biggest theories about the universe's first stars. It's forcing a serious reassessment.
Okay, so let's start with the basics of the signal itself. What exactly is a GRB? And what makes this one, GRB 250314A, so special, besides its insane distance?
So GRB stands for gamma ray burst. These are, and I'm not exaggerating, the most powerful and energetic events in the universe.
People sometimes call them fireworks in space, right?
They do, but the energy involved is just astronomical. This one, 25031VA, it lasted for about 10 seconds.
Which, amazingly, puts it in the long duration category.
It does. 10 seconds is actually considered a long burst, and that usually tells us it came from the death of a truly massive star.
Right. So tell us a bit more about gamma rays themselves. Why are they considered such a significant form of light?
Because they are just pure aggressive energy. You look at the electromagnetic spectrum, radio waves, visible light, X-rays, gamma rays are at the very, very top. Way more powerful than even X-rays.
And they don't just happen, right? You need something pretty extreme to create them.
Extremely extreme. You're talking about events like the hyperspeed collapse of an enormous star as it explodes, an event that often creates a black hole.
So whenever we talk about this kind of power, this kind of radiation, the question of safety always comes up. Was there any danger to us here on Earth?
That's a great question, and an important one. Gamma rays are definitely damaging. They can mess with your cells, your DNA. But this burst, absolutely zero danger to us.
Why is that?
Just the distance. Over 13 billion light years of travel. That focused beam of energy spreads out, it weakens exponentially. So by the time it gets to us, it's just a faint, identifiable pattern for our instruments.
So we're detecting the echo, not feeling the blast.
Exactly, a very, very old echo.
And echoes from that far back are, as we've said, incredibly rare. Why has it been so hard to catch these things from the universe's first billion years?
Well, a few reasons. The universe was smaller, stars were scarcer. But the main thing is alignment. The jet of gamma rays from the explosion has to be pointing almost perfectly at Earth.
Like looking down the barrel of a cosmic gun.
Precisely. If it's off by just a tiny bit, we miss it entirely. The source material for this dive points out that in 50 years of looking, we've only found a handful from that early period.
And the lead author of the study, Andrew Levan, he called this one very rare and very exciting.
And for very good reason. It's like finding a specific needle in a haystack the size of the observable universe.
So that explains the rarity. Okay, let's get into the detection itself. How did this all unfold? Because it wasn't just one satellite seeing one thing, right? This was a whole timeline.
Right, a collaborative effort.
So the initial discovery was on March 14th, 2025. The first instrument to spot the flash was the SVOM satellite. SVOM, that's the Space Variable Objects Monitor, the joint mission between France and China.
That's the one. It's specifically designed to catch these sudden high-energy flashes. It sees that 10-second burst, and that automatically triggers a global alert to astronomers everywhere.
Okay, so the alarm bell rings, but that's not the end of the story.
Not at all. Catching the gamma rays, that just tells us, something happened over there. To really understand the star that died, to calculate its distance, you need what's called the afterglow.
And this is where the James Webb Space Telescope comes in. But there was a bit of a delay. The signal was detected in March, but Webb didn't confirm it until the summer, about 3.5 months later. Why the wait? Wouldn't the signal just be gone?
It's a great question, and it gets to the heart of how this all works. The gamma ray part, the initial flash, that's gone almost instantly.
Right.
But when a star like this explodes, it throws out a shell of material, and that material continues to glow in lower energy light for days, weeks, sometimes even months.
Ah, so that's the afterglow.
That's the afterglow, and that's what the Webb telescope was waiting for. You can't really do detailed science on the initial flash. It's too fast. You need to analyze the light from the fading afterglow.
It's like you see the lightning, but you study the thunder.
That's a perfect analogy. And Webb captured these incredibly detailed images and measurements of that fading light. And by analyzing its unique signature, its spectrum.
They could calculate the redshift.
Exactly. They saw how much that light had been stretched by the expansion of the universe, and that confirmed its colossal distance. It proved, beyond a doubt, that this wasn't some local event or random noise. This was a massive star dying at the edge of observable time.
The power of that telescope is it's staggering. Okay, so we've established it. We're looking at a star that died 13 billion years ago. But this is where the detective story really pivots, isn't it? Because the star wasn't what they expected to see.
Not at all. This is the big cosmic mystery. When we look that far back, 730 million years after the Big Bang, we had a very strong theoretical expectation of what a star's explosion should look like.
An expectation based on what, exactly?
It's based on the material that was available back then. We expected to see what's known as a population third star.
Population 3, that's a key concept, right? Explain that for us.
It is. So right after the Big Bang, the universe was pristine. It was almost entirely hydrogen and helium, and that's it. There were no heavy elements, what astronomers call metals, which is anything heavier than lithium.
So no carbon, no oxygen, no iron.
None of it. And population third stars were the very first generation born from that pristine gas.
So how would a star made of just hydrogen and helium be different from a star like our sun, which is packed with heavier elements?
Well, those heavier elements, those metals, they act like stabilizers. They help regulate a star's internal temperature and fusion. Without them, the theory suggested these early stars had to be, monsters.
Monsters.
Hundreds, maybe even thousands of times the mass of our sun. They would have burned incredibly hot, lived very short, very violent lives, and their deaths. Their deaths were expected to be chaotic and just profoundly unusual.
Okay, so the expectation was a cosmic monster of an explosion.
Yes.
And what did we actually find with GRB 250318A?
We found a standard model. That's the punchline.
A standard model.
The research, published in Astronomy and Astrophysics, showed that this star, dying when the universe was barely formed, looked remarkably similar to modern supernovae, the kind that happened billions of years later in galaxies that are rich with all those heavy elements.
So we went looking for this chaotic, pure hydrogen giant. Yeah. We found something that looked normal.
Depressingly normal, in a way. The key evidence was, first, the overall brightness of the supernova. It was standard. Second, its decay rate and the specific signature of its radiation matched what we see in the local universe.
And there's a great quote about this.
Yes. Professor Neil Tambier from the University of Leicester, he just put it plainly. He said, Webb showed that this supernova looks exactly like modern supernovae.
Wow. So if a star that early behaves like a modern star, what does that do to our understanding of how stars evolve?
It means we might have to speed up the timeline significantly. If this star wasn't one of those metal-free population third stars, but was instead a metal-enriched one...
then that means other stars must have come before it.
Exactly. Generations of stars must have lived and died even faster than we thought, seeding the universe with heavy elements rapidly enough to create a star that was structurally modern, only 730 million years after the Big Bang.
Okay, let's tie this into the bigger picture.
Yeah.
Why should you, listening at home, care about one star that died 13 billion years ago? What does this mean for the universe as a whole?
Well, it really affects everything that came after. We still have this massive knowledge gap about that first billion years. That's the era when the first galaxies were being built, when the building blocks for, well, for us, for planets and life were being forged.
And supernovae are those forges. They're not just destructive events, they are the element factories of the universe. They spread iron, oxygen, carbon all across space.
Absolutely. That element connection is profound. If the way these ancient explosions worked is similar to modern ones, it has huge implications for how quickly the universe became chemically complex.
Which would affect,
Right.
what, the speed of galaxy formation?
Yes, that's a big one. This rapid enrichment of elements changes how cosmic gas cools down. And that cooling rate dictates how fast new stars can form and, crucially, how quickly the first galaxies could stabilize and build complex structures, like the spiral arms we see today.
So this one finding suggests that the whole process of building a complex universe might have been more efficient, maybe faster, than our models predicted.
That's the main implication, yes. The universe may have gotten sophisticated much, much faster than we thought. Our models, which were based on those chaotic population third explosions, might need a serious rewrite.
And presumably with a Webb telescope, this is just the beginning.
Oh, absolutely. Webb is just getting started here. Scientists fully expect to find even more of these signals from that ancient era. They're pushing to find events from when the universe was just 2 or 3% of its current age.
So each one of these isn't just an observation.
No, each one is actively rewriting our cosmic history books. It's showing us that complexity might have been the rule, not the exception, even at the very dawn of time.
This has been just a fascinating journey. We started with this mysterious 10-second flash of gamma rays, GRB 250314A. We traced it back 13 billion years and found that a star that died near the dawn of time behaved in this surprisingly modern way.
It really is an incredible insight into how quickly the fundamental rules of the cosmos, settled down. It seems to have bypassed that whole expected era of metal-free giants.
And that speed, as you said, has huge implications.
It does, and it leaves us with the final, really provocative thought that we wanted to share with you. Think about this. If stars 730 million years after the Big Bang were already sophisticated enough to produce these element-rich, modern-style supernovae,
Right.
then those first true population-3 stars must have exploded even earlier, and with such incredible efficiency that they changed the chemistry of the entire cosmos almost instantly. So what does that tell you about the initial conditions of the Big Bang itself?
What does it tell us?
Well, it forces you to ask the question, was a mechanism for creating complexity just built into the universe from day one? Did it allow that elemental foundation for life to emerge at a much, much quicker pace than anyone had ever imagined? That's the question this one single 10-second signal forces us to ask.
Okay, one question for you. Why does this ancient supernova look almost identical to modern supernova? Don't forget to comment it. Thanks.